RAG architectures. Corrective RAG, corrective retrieval augmented generation, is an advanced variation of standard retrieval augmented generation designed to improve answer quality by detecting and fixing retrieval mistakes during generation. Core idea. In classic RAG, 1. Retrieve documents. 2. Feed them to an LLM. 3. Generate an answer. The problem. If retrieval is bad, the answer is wrong. Corrective RAG adds a feedback loop. It evaluates whether retrieved documents are useful. If not, it corrects retrieval before answering. How corrective RAG works. 1. Initial retrieval. Query vector database. For example, face, pinecone, get, top K documents. 2. Relevance check. Key step A model or heuristic checks. Are these docs actually relevant? Are they sufficient? This can be done via LM scoring, cross-encoder re-ranker, classification model. 3. Correction strategy. If retrieval is poor, the system can query rewriting, reformulate the query. Example, how does RAG fail? Failure modes of retrieval augmented generation. External search. Use web search or another index. Additional retrieval. Increase K. Use hybrid search, BM25 plus vector. 4. Final answer generation. Only after good enough context is found. LM generates a more reliable response. Pipeline comparison. Standard RAG. Query, retrieve, generate, corrective RAG. Query, retrieve, evaluate, fix retrieval, generate. Why it matters. Corrective RAG solves major real-world issues. Hallucinations from irrelevant context, missing critical information, over-reliance on first retrieval, improves factual accuracy, more robust in production systems, better for domain-specific chatbots, like your RAG project. When to use corrective RAG. Use it when data is noisy or incomplete. Queries are ambiguous. High accuracy is required. For example, legal, medical, technical. Speculative RAG. Imagine a system that doesn't just retrieve information and generate an answer, but actually thinks ahead. This is the idea behind speculative retrieval augmented generation, or speculative RAG. To understand it, let's briefly recall traditional retrieval augmented generation. In standard RAG, a system retrieves relevant documents from a knowledge base and then uses a language model to generate a response based on those documents. Simple, efficient, but not always optimal. Why? Because the system retrieves information before it fully understands what kind of answer it truly needs. Now, imagine flipping that process. Instead of starting with retrieval, the system begins by generating a draft answer. This draft is not final. It's a speculation, a rough guess, an informed hypothesis. This is where speculative RAG becomes powerful. The system analyzes its own draft and asks, what information would I need to verify or improve this answer? From that speculative response, it extracts key facts, claims, and uncertainties. Then, it performs retrieval, not blindly, but guided by its own reasoning. In other words, retrieval becomes intent-aware. Instead of searching for documents that match the query, the system searches for documents that validate or challenge its own thinking. Let's walk through the process step by step. First, the user asks a question. Why is my Kubernetes deployment randomly restarting pods? Second, the model generates a preliminary answer, its best guess without external help. Pods usually restart due to liveness probe failures, out-of-memory errors, or crash loops caused by application bugs. This is a speculative answer. It might be right, but it's not verified. Third, the system inspects this draft and identifies weak points, missing facts, or areas of uncertainty. Is it really a liveness probe issue? Could it be killed? Are there other causes? Node pressure? Config errors? It identifies uncertainties and missing evidence. Fourth, it constructs targeted retrieval queries based on those gaps. Instead of a generic search like Kubernetes pod restarting, it generates focused queries. Kubernetes pod restart reasons killed versus crash loop back off. How to check liveness probe failures. Kubernetes. Rachel, describe pod restart causes explained. Fifth, it retrieves high-quality, focused information. And finally, it produces a refined, well-supported answer. So the pipeline looks like this. Query, then speculate, then retrieve, then refine. Why is this useful? because it aligns retrieval with reasoning. Instead of hoping the right documents appear early, the system actively seeks what it needs. This leads to more precise answers, better fact-checking, and fewer hallucinations. Speculative RAG is especially powerful in complex domains. Think about scientific research, legal analysis, or advanced engineering questions. In these cases, the right answer often depends on subtle details that a simple retrieval step might miss. But a speculative system can identify those details in advance and go looking for them. Of course, this approach comes with trade-offs. It requires more computation. It introduces additional steps, and the quality of the final answer depends on the quality of the initial speculation. If the first draft is too far off, the retrieval process may follow the wrong path. But when designed carefully, speculative RAG represents a major step toward more intelligent AI systems. Systems that don't just respond, but reason, reflect, and refine. In the evolution of AI, this marks a shift from passive retrieval to active inquiry. And that shift brings us closer to machines that don't just answer questions, but truly understand how to answer them well. Agentic RAG. Now let's move one step further. Beyond retrieval, beyond speculation, into systems that can actually act. This is the idea behind Agentic Retrieval Augmented Generation, or Agentic RAG. At its core, Agentic RAG builds on retrieval augmented generation. But instead of a fixed pipeline, it introduces something new. An agent. So what is an agent? An agent is a system that can make decisions, choose actions, and adapt its behavior based on a goal. Instead of following a predefined sequence like retrieve, then generate, an agent decides what to do next. In Agentic RAG, the system doesn't just retrieve information once. It can search multiple times, decide when more information is needed, use tools like APIs or databases, evaluate its own progress, and iterate until it reaches a good answer. Think of it as giving your RAG system a brain, not just memory. Let's look at a concrete example. Imagine a user asks, what's the best way to deploy a Node.js app on AWS with high availability and low cost? A traditional RAG system would retrieve a few documents and generate an answer. But an agentic RAG system behaves very differently. First, the agent interprets the question and sets a goal. Provide a deployment strategy balancing availability and cost. Then it begins reasoning. I might need to compare multiple AWS services. Step 1. First action. Retrieve. The agent searches for 1. AWS deployment options for Node.js. 2. Cost comparisons. 3. High availability patterns. Step 2. Reflection. After reading the results, the agent realizes, I have general info, but I'm missing pricing details and trade-offs. Step 3. Second action. Targeted search. Now it refines its approach. AWS ECCs versus Lambda cost comparison. When to use Kubernetes versus serverless AWS. Step 4. Tool use. The agent might even call a pricing API or simulate expected traffic costs. Step 5. Synthesis. Finally, it produces a structured answer. For low cost and high availability, AWS Lambda with API Gateway is often optimal for variable workloads. For more control, ECS with Fargate provides a balance between scalability and cost. Kubernetes offers maximum flexibility but introduces operational overhead. Notice what happened. The system didn't just retrieve once. It planned, acted, evaluated, and refined. This is what makes Agentic RAG powerful. It transforms a static pipeline into a dynamic process. Instead of query, retrieve, generate, we now have query, plan, act, observe, think, act again, and only then generate. This loop is often called a reasoning action cycle, and it allows the system to handle much more complex tasks. Agentic RAG is especially useful when the question requires multiple steps. Information is incomplete or scattered, external tools are needed, or accuracy is critical. But it also comes with challenges. It's slower, it's more complex to design, and it requires careful control to avoid unnecessary actions. Still, it represents a major shift from systems that answer questions to systems that solve problems. And in that shift, we move closer to AI that doesn't just respond, but works alongside us. GraphRag. So far, we've explored systems that retrieve documents. But what if the knowledge we need isn't just stored in text, but in relationships? This brings us to Graph Retrieval Augmented Generation, or GraphRag. At its core, GraphRag extends retrieval augmented generation, but instead of retrieving flat chunks of text, it retrieves connected information from a structured network known as a knowledge graph. So, what is a knowledge graph? It's a way of organizing data as entities and relationships. For example, AWS Lambda is a service. Amazon provides AWS Lambda. AWS Lambda is often used with API Gateway. Each of these facts forms a connection. Together, they create a graph, a web of meaning. In traditional RAG, the system searches for documents that match your query. But in GraphRag, the system can traverse relationships. It doesn't just find information. It follows connections. Let's make this concrete. Imagine a user asks, how is Kubernetes related to Docker and cloud providers? A standard RAG system might retrieve articles mentioning Kubernetes and Docker, but it may miss the deeper structure. A GraphRag system does something more powerful. First, it identifies key entities, Kubernetes, Docker, cloud providers. Then it queries a knowledge graph. It might discover Kubernetes architects containers, Docker creates containers, cloud providers like Amazon Web Services and Google Cloud host Kubernetes clusters. Now, instead of isolated documents, the system has a connected map of knowledge. Finally, it generates a response like this. Docker is used to build and run containers, while Kubernetes archetypes those containers at scale. Cloud providers such as Amazon Web Services and Google Cloud offer managed Kubernetes services, allowing applications built with Docker to be deployed and scaled in the cloud. Notice the difference. The answer isn't just based on text similarity. It's based on relationships between concepts. This is what makes GraphRag powerful. It enables multi-hop reasoning, better context understanding, more precise and structured answers. GraphRag is especially useful when knowledge is highly interconnected. Relationships matter more than raw text. Questions require reasoning across multiple entities. Think of domains like recommendation systems, fraud detection, biomedical research, complex infrastructure systems. Of course, there are trade-offs. Building and maintaining a knowledge graph takes effort. It requires structured data, and graph travel can be computationally expensive. But when the problem demands understanding connections, GraphRag provides something unique. It doesn't just retrieve information, it navigates knowledge. And in doing so, it brings us closer to systems that don't just read the world, but understand how everything in it is connected. A knowledge graph is a way of storing information as entities, things, relationships, connections between things, graph database, used for knowledge graphs, nodes, entities, edges, relationships, examples, Neo4j, Amazon, Neptune, contextual RAG. So far, we've explored systems that retrieve information. But what if the real challenge isn't finding data, but understanding the context behind a question? This is where contextual retrieval augmented generation, or contextual RAG, comes in. At its foundation, contextual RAG builds on retrieval augmented generation, but it introduces a crucial idea. Retrieval should depend not just on the query, but on the context surrounding the query. So what do we mean by context? Context can include previous conversation history, user intent, user preferences, location or environment, even the task being performed. In traditional RAG, the system treats every query as isolated. But in real life, questions are rarely isolated. They are part of a conversation, a goal, a situation. Let's look at a concrete example. Imagine a user is chatting with an AI system. First, they ask, I'm deploying a Node.js app on AWS. Then they follow up with, what's the cheapest option? A standard RAG system might interpret the second question in isolation. It could retrieve general information about cheap cloud services, missing the fact that the user is specifically talking about Node.js on AWS. But a contextual RAG system behaves differently. It remembers the earlier message. It understands that the cheapest option refers to deploying a Node.js application on AWS. So when it performs retrieval, it enriches the query. Cheapest way to deploy Node.js app on AWS. Now the retrieved information is far more relevant. The final answer might be, for a Node.js app on AWS, the cheapest option is often AWS Lambda with API Gateway for low or variable traffic. For more consistent workloads, AWS EC2 with reserved instances may be more cost-effective. Notice the difference. The system didn't just respond to the last message. It responded to the full context. This is the essence of contextual RAG. It transforms retrieval from a static lookup into a context-aware process. Contextual RAG is especially powerful in chatbots and assistants, multi-step workflows, personalized systems, long conversations, but it also introduces challenges. Context must be managed carefully. Too little context leads to poor answers. Too much context can introduce noise or slow down the system. Designing a good contextual RAG system means deciding what context to keep, what to ignore, and how to represent it effectively. In many ways, contextual RAG mirrors human thinking. When we answer a question, we don't just hear the last sentence. We remember the conversation. And that memory is what makes understanding possible. Adaptive Retrieval Augmented Generation, or Adaptive RAG. At its core, Adaptive RAG still builds on Retrieval Augmented Generation. But instead of following a fixed pipeline, it introduces a key capability. The system can change how it retrieves and generates based on the situation. In traditional RAG, the process is static. Query, retrieve, generate. The same steps happen every time, regardless of the complexity of the question. But not all questions are equal. Some are simple and need little context. Others are complex and require deep retrieval, multiple sources, or even reasoning across documents. Adaptive RAG recognizes this difference. It asks, how much retrieval do I actually need for this question? Let's look at a concrete example. A user asks, what is Docker? This is a simple question. An adaptive RAG system might decide, no retrieval needed. I already know this. And it generates a direct answer. Now consider a different question. What are the trade-offs between Docker and Kubernetes in production systems? This is more complex. Now the system adapts. It performs deeper retrieval. It may gather multiple documents. It may compare sources. And for an even harder question, why did my Kubernetes deployment fail after switching from Docker Compose? The system might go further. Retrieve technical diagnostics, expand the query, possibly iterate multiple times so the pipeline is no longer fixed. Instead, it becomes query, then decide, then retrieve if needed, then adapt, then generate. This decision step is what makes the system adaptive. It can choose whether to retrieve at all, how many documents to retrieve, which retrieval strategy to use, whether to refine or retry. Why does this matter? Because it improves both efficiency for simple queries, accuracy for complex ones. Adaptive RAG is especially useful in real-world systems where queries vary in complexity, latency matters, cost must be controlled. Of course, it introduces new challenges. The system must make good decisions. If it underestimates a question, it may skip needed retrieval. If it overestimates, it may waste time and resources. But when designed well, Adaptive RAG creates a more intelligent system, one that doesn't treat every question the same, but responds with the right level of effort. In a way, it mirrors human thinking. We don't research every question in depth. Sometimes we answer instantly. Sometimes we dig deeper. Adaptive RAG brings that flexibility into AI, and that flexibility is what makes systems truly efficient and scalable.